Okay. All right. Hi, everybody. My name is Doug Fawley. I am an engineer at Google, and I work on the Go language implementation of gRPC. And today I want to talk about some best practices for running gRPC services. The concepts should apply to pretty much all languages, but the code examples will be in Go, and some of the concepts will be Go-specific kind of concepts. So first of all, for those who don't know, gRPC, it stands for, the G actually does not stand for Google. The G stands for a different word for every release we do. So the first one actually stood for gRPC, and then RPC being remote procedure call. It is a high-performance, open-source, standards-based, feature-rich RPC framework. That's a lot of buzzwords in one sentence. Basically, it's a way of sending messages across networks. And it's an open source version of the stubby RPC system that we've been using internally at Google for the past, 15 or 20 years or so. And it's under active development, and the latest release is version 1.3. So this is a typical Hello World style example. On the left-hand side is an example of what the proto file would contain that describes the service and the RPCs that it provides. Here you can see there is a math service defined which has a division RPC, and it accepts a request message and returns a response message, and those are defined below. On the right-hand side is the actual implementation of our math service. It's got a server type that is defined that has a method on it that implements the method required for this type to be registered as a gRPC service, as a math service. And then the main function at the bottom shows how to listen on a TCP port and register the server and start it up. And yeah, this is pretty much all it takes to do a simple Hello World style solution. But normally things aren't this simple when you get to the real world. Things get a lot more complicated, and your concerns become how to run your service reliably in a secure way that's performant, does correct error handling, et cetera, et cetera, et cetera. And these are things that are often left out of the getting started documentation. So what I wanted to talk about today was how to do some of these things and what kind of best practices you can follow in your services in order to resolve some of these issues and cover some of the gaps that are missing between the Hello World example and a real world actual deployment. And to top it all off, when you get to the real world, complexity almost never looks like the standard, I have one client that talks to one service, that thing that the Hello World example always presumes. It ends up being something more complicated, like the picture at the bottom where you have a bunch of services all talking together. And so some of these concerns become even more important when you have those types of deployments. So these are the summary of all the things that I want to touch on today. I apologize if some of the transitions won't be smoothly. It's just going to be a list of things that I'll be running through. And hopefully some of them will be pretty obvious to many of you here, but hopefully there will be some things that many of you haven't really considered before. So yeah, with that, I like to start with API design, because I think that if you start off with a poor API, then you can really run into trouble trying to actually implement something that is reliable on top of that. So it's a good idea to start with the API design and really make sure that you're following best practices there before you move on and start implementing. So the first concept for API design is idempotency. This means that it is safe to retry RPCs, not knowing whether or not they've completed. And so the reason for that is because as a client talking to a service, you don't necessarily know whether the operation that you're attempting has been committed or not before an error occurs. So you want to make sure that your RPC API enables you to proceed even when you don't know for sure whether that's happened, and allow clients to retry calls when there's any type of a failure. So for example, if you're transferring money and you have an RPC to initiate that, this example request and response here shows that you can provide some basic information, a sender, a recipient, and an amount of money to transfer. But obviously this is bad because when you perform this RPC, if there's some kind of an error like a deadline exceeded, you don't know whether or not the money's been sent. So as a client, you could retry it. Now that'll result in multiple transactions happening. So obviously we want to avoid that. And we can resolve the issue by adding a timestamp, for example, to the operation, or a globally unique ID, or some kind of a transaction token that the server can use to determine whether or not the operation has been performed, and then not perform the operation a second time if it turns out that it's redundant. It's also important that your response be identical whether this is the first call or a subsequent call. And the reason for that is because you don't want your clients to have to implement special case logic to know whether or not this response is a first response type of message or some kind of a subsequent thing, and have different logic depending on that. So you want to make sure to always return the exact same response message. Let's see, another issue is performance. You have to think about that when you're designing your API. If repeated fields can be a particular problem. Repeated fields are essentially lists that have no bound on their size in protocol buffers. And if you have one of these in your requests, that basically means that your service is allowing someone to specify potentially an unlimited amount of work for your service to perform. And this can be a problem because obviously you don't want to do an unlimited amount of work. We had a RPC on a team that I worked on before where we offered the ability to batch multiple database transactions into a single call. And we expected most users might send 20 or 50 operations just as a convenience. We offered this, but we did have one user that thought like 5,000 would be reasonable, and that leads to a lot of problems down the line. So it's important to set limits on these things and check them when you're validating incoming requests, and error out early if you see something you don't want to handle. Conversely, in a response, wherever you see a repeated field that you want to send back, you should stop and think about what that represents, and make sure that you're not going to be returning an unbounded amount of data potentially too. And if you are, then you want to make sure your API supports pagination so that users can do repeated queries and get a section of the result back each time. Or alternatively, you can utilize a streaming RPC where the results are sent back one result at a time. Another issue with performance to think about is long-running operations. So anything that takes on the order of a couple tens of seconds, I would recommend not doing that in a synchronous RPC, because the longer an operation takes to complete, the more likely it is that it will fail at some point, because either the machine goes down or the network connection gets dropped, or any other number of things. So when you find yourself wanting to do this amount of work in an RPC handler, you should consider how else you can do this. For instance, by performing the operation in the background, return from the RPC as quickly as possible, and then perform that operation in the background and deliver the results through some other mechanism besides the RPC response. So you can use either a callback or an email or publish a message to PubSub. Or you can also, in your response message, provide a tracking token back to the user, and then they can call a different RPC in your service to check on the status of that operation. But yeah, pay attention to those long-running operations. Still on API design here, default values are important to consider. With protocol buffers, if someone doesn't specify a setting for a field, that field will go back to the default value of the 0 value for that type, so an empty string or a 0 integer. And for enums, the 0 value becomes the 0 entry in the enum definition, and you can take advantage of that by making the 0 value some kind of an unset, unknown, unspecified. That can be an indication to you that the user didn't set the field when you wanted them to make a decision about what that should be. It does make sense, though, to specify default behavior that is the most common behavior. And so as an example of that, if your operation is a database query, for instance, then you might make the sort ordering an enum, and the default there can be ascending, and that's a reasonable thing to do. Another reason why you might pick less common default behavior, though, is to maintain backward compatibility. And so if your service already has this RPC and you want to add a new field that offers new functionality to the user, you obviously need to make sure that existing users aren't broken when you add this. So just make sure the default value matches up with the old one. Because even if you're running like the full stack yourself and you own the clients and you own the services, unless you are intending to have planned downtime, then you basically can't restart your clients and services all at the exact same moment. So when you're doing this, make sure you add the new functionality, do a rolling reload of your servers, and only then begin to reload your clients. And then just be careful when you're introducing new features like that, because inevitably you will need to roll back your servers if you find a bug. And so keep in mind that if you've already started releasing clients that use those features, then you're going to be broken. Let's see. So last thing on API design that I'm going to talk about is errors. So in gRPC, errors are a first-class concept. What that means is for any RPC you send out, the response will come back as either the payload data in the message for the type that you defined for that RPC, or you'll get back an error. And the error includes a status code, which is canonical and shared across all the different languages that implement gRPC. Then you get a status message, which is an arbitrary string that you can set. And then recently we added the ability to send arbitrary structured data along with the error that you can attach to the errors that you send back and then check on the client side. So it's best to use this functionality and not try to return error information in the response, because if you don't have a failure in the RPC itself, but the result message says that there was a failure, now your client logic becomes a little more complicated, because you have to check to see whether the RPC succeeded, and then if it actually succeeded, check to see if the response indicates that the operation you were attempting failed. And that can get really complicated. So it's best just to keep it simple and use the built-in error system. Along with error handling, it's a good idea to avoid trying to batch multiple separate operations into a single RPC. And the reasoning behind this is that error handling can become complicated in these situations too, because if you're performing multiple, for instance, database transactions in a single call, now you need a way of communicating back to the caller which operations succeeded, which ones failed, which ones maybe you didn't even attempt. And so that can get really hairy, especially in the context of, if you don't manage to send the result back because there was a deadline exceeded error. Now the client has to figure all this out. So in these cases, I would recommend use a streaming RPC where each request message indicates a single operation that you want to perform, and then each response to that particular message would indicate a single result. And that's one place where maybe you do want to put error messages into the payload, because the errors are per stream. So for a streaming RPC, you would have to terminate the entire stream in order to indicate that an error happened. But the other option is to use multiple calls instead. So initiating an RPC call is fairly lightweight. So it should be fine to just tell your users to perform multiple calls when they want to perform multiple operations. And you can have multiple concurrent RPCs in flight. That's fine. And that keeps things simple for error handling. So on the topic of error handling, the requisite Douglas Adams reference here, don't panic. Basically, any kind of a panic means that your server has crashed and now you're not serving traffic anymore. So this should be fairly obvious, but especially in languages that are not Go, it's pretty common to throw in assertions or checks that will actually crash your application if you violate them. And yeah, I've run into this situation in the past a few times. It's remarkably prevalent how often this happens. So yeah, just know that even if you're not in your application doing these things, maybe look at the libraries you're using and try to figure out if those have checks in them and avoid those at all costs. Panic is appropriate in certain cases. If you can detect that there's been memory corruption, or if you've run out of memory, or if imminent data corruption in your database is about to happen, then sure, go ahead and panic if that's your only way out of the problem. But otherwise, always best to return an error. And then just a word of warning is obviously, null pointer exceptions are, to be considered as a panic, just like this. In Go, for protos, it can be a pretty common thing to have proto messages, and when you have nested proto messages, you can have nils if they're not set. And if you use the getters on the proto messages, those handle nil receivers just fine and don't panic. But if you forget to do that somewhere in your code, you can end up with crashes and causes lots of problems. So another thing to talk about for error handling is what to do when services that you are using as a service or libraries that you're using return an error. Don't follow the pattern or anti-pattern of if err not equal nil, return error from your RPC's handler. You really want to convert all of your errors into things that are appropriate for your users to be able to make sense of what happened. And you want to make sure you set the status code correctly in that error to something that will give the user an indication of whether they should retry the RPC or whether they should give up and file a bug against you or whatever. So at the bottom, there's an example of how to do this for making another gRPC call from your gRPC service. So there's a from error method that you can call to make sure that the result that you got back from that RPC call was the right type of an error. If not, you can return an internal error back to your caller that's not expected to happen. And then you actually want to look at the error codes that came back from the service that you called and make sure you're translating those appropriately. And so the example down here is taking an invalid argument error, which means that my service, when I made an outgoing call, I gave illegal arguments to that service. That's not the fault of the user that called me, so I'm going to translate that into an internal error, when I return that, so that they know that it's my fault and not theirs. Okay, switching gears a little bit, deadlines. Deadlines are really important, and deadlines are how a client communicates to a service when it needs an answer by, and it allows the client and the service and all of the other services down the chain, assuming your context is forwarding this deadline correctly, it allows them all to stop at the same time if they can't meet that deadline. So there's a couple ways that you can set a timeout. You can either set it as a duration in the future, the example on the left, or you can set an absolute time, as in the example on the right. And then that information gets set into this context object, which is part of the gRPC API used for clients and services. And so then you attach that timeout to the context and pass that context into your outgoing RPC call. And then that gets received on the server side. Servers care a lot about deadlines too. If your deadline is not long enough, then as a service, you can know to abort early and not attempt an operation. So it's a good idea to check deadlines to make sure you have enough time before you start performing an operation. And conversely, if you have no deadline, that's a very bad thing, actually. It means that the RPC can sit there and stall with you indefinitely, which could be a problem. Or if your deadline's just too long, it means that you're using up resources that you might not be intending for too long. So here's an example of how to, in Go, retrieve a deadline from the incoming context in the handler. And then you can also check how far in the future it is. The deadline's returned as the absolute value always, and it's carried and propagated in the context in that form. But then you can check how far in the future that is, and then error out if there's not enough time or if too much time was specified. Now, as a service that's making calls to other services as part of an interconnected system, you often need to propagate this deadline that the client gave you when you're making your outbound calls. And you may be making many outbound calls, and so you need some kind of a strategy for specifying to all the calls that you're making what that deadline is. So the first most obvious thing you can do is just reuse the context as it was given to you when you're making outbound calls. And this is pretty simple, and it works, and it lets, for each call, it lets everybody know what the deadline that your client had. But it does have one drawback, which, depending on your use case, could be a small one or it could be a big one. And that's that you don't ever terminate early, even if you're sure that the operation isn't going to complete. So if in the process of performing the first call, you use up almost all of your time, and you're not going to have enough time left to make calls 2 and 3 here, then you could, in theory, return early and give up at that point. But this implementation would keep going because the deadline has not been reached yet, and so you would perform the second call, and maybe that one times out. So it's not super ideal, but it is convenient. Another choice that I've seen employed is to basically measure the performance of all the services that you're calling, and then set a deadline that's appropriate to each one of those calls. So in this example, if the first call takes, usually it completes within 100 milliseconds, then you can apply a 100 millisecond timeout to the first call, and then 50 and then 100 for the subsequent ones. So this is also fairly easy to implement, and it does give you that benefit of returning early in case there's not enough time left to finish an operation and one of those calls is taking a long time. But the problem is that it may cancel too early. And so even if you're using something like the 99th percentile latency number for those deadlines, 99% times 3 different calls means you're going to fail your RPC now 3% of the time when you do this. So you have to use really conservative numbers if you go with this approach. And then the third method for this that is the most ideal in my opinion, but probably also one of the hardest to implement, would be to try to determine how much remaining work you're going to have to do after the first operation completes and set that as your deadline when you make your first call. And then when you perform your second call, you do the same thing. So you work backwards about how much remaining work you have to do. And so for the first call, we basically take whatever the client's deadline is, and we subtract 150 milliseconds, which was the time for the 2 subsequent calls, on a good day, and then we use that as the deadline to the first call. So this lets your first operation take as long as it needs, as long as it returns within time to, assuming the other services are performing as expected, everything will work fine. So the problem here, though, pretty obviously, is that this can be hard to maintain. So if you want to reorder calls or add something in the middle there, you have to go update all the places where you're setting the previous deadlines. Okay, rate limiting. So rate limiting is a potential problem for all services, pretty much. If you're getting too many requests from the same user, then they can be denying your ability to handle requests from other users. So to keep things fair, we like to apply rate limits. The way that you do that in gRPC Go is you can take advantage of this hook that we have called the tap handler. This is executed basically right after the message makes it to the server. So before the payload actually is even decoded, and possibly, depending on the size, before it's even been received entirely. So this is the best place for a rate limiting kind of check, because it prevents the server from using too many resources in order to perform the rate limiting. So below is an example of how to use that. I've used the xtime rate package, which provides a limiter type, which is a pretty simple but effective way of doing this. But essentially, the context, which is provided as a parameter to your tap handler, contains information about the user and their credentials and everything. So you can extract that from there. I haven't shown that. And then you can just apply a rate limiter for each user that calls your service. Obviously, you would want to make sure your map has a RW mutex or something like that on it, because maps aren't thread safe here. But you can assign a new rate limiter if one doesn't exist, and then you just check the allow method. If the user's over their allowable rate limit, then that returns false, and you can return an error immediately back to the caller. So on the other side, as a responsible client, you want to implement your own rate limiting, and that should match whatever the server's enforcement is. So keep that in mind. And it's just as easy to do rate limiting on the client side as it is on the server side. And you can use the exact same xtime rate package for that, and the same limiter object, in fact, which you can initialize in the exact same way. It's just that instead of calling the allow method, which determines whether or not you're allowed to proceed, you call the wait method, which blocks. And note that the wait method takes a context, which allows the wait to break early if the context deadline is exceeded. So recommend doing this when you're making outgoing calls. And another thing I wanted to talk about was retries. So gRPC does not currently support retries, but it has been an approved RFC, and so that will be implemented in the near future. And the way that you'll set that up is through this service config feature that we have in gRPC that enables services to communicate to clients how they should contact that server and what sorts of parameters they can use. And so one of those configuration knobs will be how retries work. The retry support that will be added isn't only retries, which would be sequential calls, and then if an error comes back matching a certain error code, wait a certain amount of time and perform the call again. That's your standard retry. It also will support concurrent hedged requests, so it will actually be able to send out the same request to multiple servers at the same time, and then whatever result comes back, it will take that one and cancel the call outbound to the other services. But until then, you have to implement retries yourself, sorry. And you can do this with either some kind of a wrapper library, or you can use interceptors, which is also a good choice. And just a note is that the context that you have given to you from your clients, it's a good idea to just use those verbatim when you're doing these operations. From a previous role, we tried something where we took the deadline and split it into 3 parts and did retries in case things stalled. And that turned out to be a really bad idea, because if you abort an operation early, you don't know, it might have been just about to return. And so if you took your 10-second deadline, you split it up into 3 3-second calls, and it was just going to take 4 seconds to do your operation for whatever reason, then now you can't do it anymore. And so if you had used that 10-second deadline, you would have been done much faster. So transient errors, those should either be automatically retried by gRPC for you. In certain cases, that happens when there are connection errors. And in other transient error cases, you want to just retry those yourself when you get those errors, but don't mess around with the deadline, would be my advice. So here's an example that I used on a previous team for wrapping client calls. And this essentially does a lot of the things that I was just talking about. So it employs a rate limiter, it employs retries, and it also deals with wrapping errors when they come back. And basically the way this works is it's just a single function that you can call, and you can configure this per client that you're connecting to, or per service that you're connecting to. And so it's just a single function that you call whenever you want to make any type of RPC to a particular service. And at the bottom is an example of how it actually works. So the first thing that you would do is declare your response in the scope in which you want to use it. Then you actually call this function, and you pass it a closure that returns an error and assigns to that result from the outer scope the result of making the call. And then actually, you perform the outgoing call using the context as it's given to you, and then you return any errors that came back. And then this will be run inside of the child RPC function. And if there's an error result, if it needs to be retried, then that'll happen automatically, and then it gets converted to the right type of error that you wanted it to be, and then returned back to your function that called that. And then afterwards, now you can use resultant error as though they had come directly from the RPC call themselves. So this was pretty handy for us. Another way to implement this in gRPC is to use interceptors, and I don't have an example for that, but that's actually a pretty good idea, I think, and avoids some of the mechanics around, passing the name of the function or the name of the RPC and needing to, do this wrapping stuff. It sort of takes care of all that for you. Okay, so here's something that's more specific for Go. There are no limits on the number of Go routines that a service can have outstanding at any point in time. Basically, every time a request comes in, gRPC will handle it, and it will fire off a new Go routine in order to have your application serve it. So this can be a problem under heavy load, because with no limits comes no memory. So there's a few ways of mitigating this problem. The first of which would be to set limits, and limits on the number of outstanding connections you can have at any point in time, and also how many concurrent streams or how many in-flight RPCs you can have for each one of those. And so below is an example of how you would do that. You have to limit the connections on your listener itself, and you can do that by wrapping it in this xnet netutil functionality. And then gRPC, though, does have a way of setting the limit on the number of streams that you can have for any connection. So basically, the product of those is how many outstanding RPCs now you're limited to. So another option would be to utilize the tap handler that we talked about for the rate limiting. And that works pretty well. And you could put any number of things into that too. You don't just have to limit it to number of RPCs in flight. You could also look at your memory that you have available, or anything else that you want to use for health type checking, and be able to error out early before things start using too many resources. And then the last option is probably the ideal one, but takes a lot of effort to set up and requires that you have a lot of coordination going on around it. But you can use health reporting to have your service advertise how much memory it's got available, and then have load balancers that are monitoring the health of all of your servers and redirecting traffic appropriately. So not just a large number of requests can run you out of memory, but just a single very large request can run you out of memory. There's no inherent limits on the size of a proto message, and there's no built-in defaults, I believe, for gRPC enforcing a limit on how big of a message it will accept. And so that can be a problem, because just in the process of receiving your message, you could run out of memory. So it's advisable to set a limit on that receive message size, and you can do so when you create your server with the option up there. And I recommend figuring out a number that works for your service and setting that. And then on the way out, even small requests can result in very large responses. So consider where you have a database query as your request, and an enterprising user wants the entire database, and they do select star. Now you've got to fill in your response message with the entire contents of your database, which will probably run you out of memory before you can return. And it's even possible that maybe you can fill it all in, and then you send it back to your client. Now they crash because they don't have enough memory to hold it, because maybe your server has more resources than their client did. This goes back to the API design issue, though, and how it's hard to fix things when they start out broken. In this case, you should support pagination for this RPC, and limit the number of results that you can have, or just do a streaming mechanism there. Okay, a couple more random topics here. So logging. It seemed like a good idea when I first started at Google writing services to just start logging errors and think that, hey, maybe I'll notice that one day. Nobody reads logs. It should be obvious, but it wasn't to me, so I'm here to spread the word. If you have an error and you want to find out about it before your user reports that problem to you, then don't log it. Use monitoring for that. The caveat here is that logs actually can be really useful if you are post-processing your logs and generating alerts or metrics from that. But if you're not doing that, then logs are great for debugging. Once you've detected a problem, they can help you track it down, but they're not going to help you notice a problem. So just be careful what you use your logs for. So yeah, instead use monitoring. And I think it's really important. Use monitoring extensively. Have metrics for everything, custom metrics. Just do it. Set up alerts. It's a really good idea. And yeah, I mean, we had metrics for everything on my previous team eventually. And any kind of a like unexpected error or something like that, throw a metric on it, throw some monitoring on there, and then you can find out about your problems before your users do. And so we had this pattern that helped us remember to capture metrics for everything, and it let us capture all the RPC latencies and everything like that that were really important to be able to measure. But basically what we did is we embedded our server object inside of another struct called a server call, which would also carry information about that particular call. And then in our server handlers, we would essentially implement the actual handler logic on this type, and then our outer server handler would instantiate one of these and then make sure to defer a done function that would actually record latency metrics and things like that, and then call the real handler. And then the real handler was free to use this info method over here, which was an easy, convenient way of just recording information that was going on for that RPC with the context of the rest of the RPC carried along with that. So like the name of the RPC and how long it had been running at that time and things like that. So it's a lot of code, I know, but the idea is fairly simple. So that's basically it. This is how you can get in touch with us and find out more. You can follow gRPC.io on Twitter and visit us at grpc.io, and you can subscribe to the Google group and see the repo and come contribute. Thanks. So yeah, we have a little bit of time left for questions. No?
If you give me just a moment, I'll come mic you for your question.
Hi. The gRPC is implemented using regular sockets or UDP, TCP, DIPC, anything?
It's built on top of HTTP2,
Okay.
and so then it uses TCP. Yeah.
I see. So would that be an issue if thread-to-thread communication, if there are too many of them, scalability issue or any?
I'm sorry?
I mean, there'll be too many connections between thread-to-thread if you have, for each gRPC have one TCP connection.
Yeah, I mean, it can reasonably support, thousands of connections at a time. But yeah, I mean, if you're doing local machine to local machine, it does work for that also. But yeah, you would use it between processes, or not between processes, you would use it between binaries though, really. You wouldn't really want to use it even between like threads, probably.
Okay, so between binaries means multiple threads initiating the gRPC, they will be funneled through the one pipe, or how does it work?
Yeah, just in terms of like if you had multiple essentially services running on the same host, then you could implement those as separate gRPC services and do communication between them there. I wouldn't use it for just communication within a process, though. I would use other, like just use Go channels or something like that instead.
I see. So because it might be, I might not really be aware whether the process is local or remote.
Oh, right.
So
In that case,
yeah.
In that case, yeah. I mean, where you have something that is a service that has, a request and a response, then yeah, that would make sense.
And the performance would be determined by the kernel socket implementation for the TCP, I believe.
Right, with some overhead for the HTTP implementation and yeah,
I see. Okay,
and serializing your messages and deserializing
Yeah,
those. But I mean, you're going to pay those anyway,
I see.
presumably.
Okay.
Yeah.
Thank you.
And you expect protobufs take caring of versioning is controlled by using protobuf, right? Do you have any other things for gRPC or?
So proto isn't the only way to use gRPC. You can basically send arbitrary binary blobs over gRPC, but the way to implement it that is the easiest to get started with is to use protobufs.
My question is like versioning.
Versioning.
Versioning, software versioning. So do you control using protobufs only, right?
Yes, that's true. So yeah, there's no other versioning system that we support. No, you have to do that manually.
Okay.
Okay. All right.
Well,
Thank you.
Thanks very much, everyone.